Let's look at some Riemann Sums FRQ problems. This is number 1 off the AP Review worksheet. So we have table of values at different time intervals, and each time interval is providing us with a specific temperature in degrees Fahrenheit. Temperature of water in a tub is modeled by a strictly increasing, twice differentiable function, W. Twice differentiable just means that the second derivative exists, and visually what that means is it's just a smooth curve. W of t is measured in degrees Fahrenheit and t is measured in minutes. At time t equals 0, the temperature of the water is 55 degrees Fahrenheit. The water is heated for 30 minutes, beginning at time t equals 0. Values of W of t selected at time t for the first 20 minutes are given in the above table. So we have information about the first 20 minutes, but the last 10 minutes it's further into the problem. So part A, use the data in the table to estimate W prime of 12. Show the computation that leads to your answer. Using correct units, interpret the meaning of your answer in the context of this problem. So W prime of 12 is asking for what is basically the rate of change of temperature on the 12th minute, at the 12th minute. So we don't have W prime of t to pull that information. So the best thing that we can do is to find the rate of change between two order pairs that are close to that target of t equals 12. So we know that W prime is going to be in the units of change in temperature over change in time. So we can just do slope to find an estimation. We can do the change in temperature, so 67.9 minus 61.8, divided by the change in time. So we'll use slope to help find or approximate W prime of 12. And when we do change in temperature over change in time, between those time intervals of 5 and 9, and between 9 and 15, and we definitely want to use these two order pairs because these are the ones that are closest to 12. If we use any other order pair, we're using an approximation that is not as good as the two that are closest to it. So our answer is going to be our approximation is going to be 1.107 degrees Fahrenheit per minute, and this represents that the fact that the water temperature is increasing at an approximated rate of about 1 degree Fahrenheit per minute at the 12th minute. Okay, part B. Use the data in the table to evaluate the depth integral from 0 to 20 of W prime of t dt. Using the correct units, interpret the meaning of this integral from 0 to 20 of W prime in the context of this problem. Well, we don't have W prime in front of us, so we're not going to use Riemann sums here in this case, and we're not going to be accumulating values of W prime. But what we can do is, let's think about the fact what allows us to connect W prime to W of t, right? How can we represent this in a way that allows us to use this table, or use what's given to us? Well, recall that we have first theorem of calculus, which says that if I take the definite integral of a derivative, that process will push that derivative up to a function level, and then that's where I can evaluate my upper and lower bounds, f of b minus f of a, once that f prime turns into f. So using that same process, we can apply that for this problem. We know that the definite integral of W prime must turn itself into W of t, right? The derivative is going to turn itself into W of t. And that is helpful because now if we can convert this to be in terms of W of t, then these values are going to be usable for our problem. So let's go through that process. We know the definite integral or indefinite integral of W prime will turn itself into W of t. And once it turns itself into W of t, we plug in our upper and lower bound. So W of 20 minus W of 0. Well, W of 20 tells us the temperature at the 20th minute, and W of 0 represents the temperature at time t equals 0. So the result of this definite integral of w prime is just going to be w20 minus w0, which is 71 degrees minus 55 degrees, which is 16 degrees. And if we just think about these values in general, w20 minus w0 equals 16, that just means that the temperature rises 16 degrees between 0 and the 20th minute, because it starts at 55, it goes to 71, and it rises 16 degrees Fahrenheit. So that's all this is saying. This W20 minus W0 represents the fact that the temperature has increased 16 degrees Fahrenheit over the course of these 20 minutes. Okay, part C. The average temperature is given by this 1 over 20 integral from 0 to 20 of Wt dt. So this represents a little bit of average value theorem, right? Average value theorem, 1 over b minus a, integral from a to b of f of t. It says use a left Riemann sum with 4 subintervals to approximate this value. The 1 over 20 is just the coefficient, so the left Riemann sum is going to allow us to replace or give an approximation of this definite integral, this area under this w of t from 0 to 20. So the way that we are supposed to do this is using left Riemann sum. So we have to pick out width and height for these rectangles that we want to build. So the 4 rectangles are here between 0 and 4. That's one interval from 4 to 9, from 9 to 15, and from 15 to 20. And if we subtract each of these t values, we arrive at the width of these rectangles. So 4 minus 0, that's the width of 4. 9 minus 4, that's the width of 5. 15 minus 9, that's a width of 6, and 20 minus 15, that's a width of 5. The height that we want to choose is based off of what we have from part C. We want to use left Riemann sum. So that means for each subinterval, we want to choose the left height, the height on the left endpoint. So our first rectangle is a width of 4, because that's 4 minus 0. Our height is going to be 55 because that's the left endpoint. And then for the second interval, the width is going to be 5 because 9 minus 4. And we want to choose the left height, which is 57.1. Third interval, width of 6, height of 61.8. And then last interval has a width of 5 and a height of 67.9. So width times height, so on and so forth. This will arrive at the approximated area under the w of t graph between 0 and 20. And then we do the average value divided by 1 over 20 or times 1 over 20. And this accumulates to be 60.79 degrees Fahrenheit. So the next part is this an over approximation or under approximation of the actual average temperature? Remember, what we're doing here is just an approximation, right? This is not the actual average value, average temperature. Well, what they tell us is that this function is strictly increasing, right? So the graph is always rising. And if the graph is always rising and we're using left Riemann sum, visually you can tell that if the graph is rising and if I'm always attaching the left endpoint of my subinterval, these rectangles are going to prove to be below the graph, right? This is going to be under approximating the actual area under the graph because we see these gaps between the rectangle and the curve. So this estimation under approximates since we are using a left Riemann sum and we're dealing with an increasing graph. Okay, part D. Between the t values of 20 to 25, the function w that models the water temperature has the first derivative given by w prime. Okay, so now we have w prime that's given to us. We no longer have to rely on the table to do approximation. Based on the model, what is the temperature at time t equals 25? So let's think about something that we've seen before in the past. The idea that anytime I'm looking for a final value, I can always start with some initial value that's provided for me, and then I can add the displacement or bridge the gap between those two values. So to adjust for my function that we're dealing with, we can say w of b is equal to w of a plus the definite integral from a to b of w prime. So this represents the displacement or the accumulation of the rate of change of the temperature between my two endpoints. So now let's adapt this for our particular time intervals. The temperature at 25 minutes is equal to the temperature at 20 minutes plus however much the temperature changes between 20 and 25. And then we can do that by accumulating the rate between the 20th and 25th minute. So the 20th minute temperature is 71 degrees. That's provided for us at the beginning, at the top of the problem. We know that, temperature at the 20th minute is 71 degrees. And then if we used our calculator to find the definite integral from 20 to 25 of my w prime, this will give me how much temperature has changed between the 20th and 25 minutes. So between 20 and 25 minutes, temperature is going to rise 2.04 degrees Fahrenheit. So if I add that to my temperature at the 20th minute, what I arrive at is 73.043, which is a degree, which is the temperature of the tub of the water on the 25 minute.